I resumed the recording, I think. Yeah, I did. Okay, here we go. Oh boy. So we're talking about acetoacetic, malonic ester, all that kind of fun stuff. Kind of continuing on from where we started with aldol. An important thing to remember for this one, for these like reactions, is like they're similar to Claisen, and that they all have to have the same like matching base. And so whatever you used for your ethyl or methyl or whatever it is that's right here, you see what I'm circling. Um, you need to make sure you use that again as like a base to pluck off your acidic hydrogens from this guy. Otherwise, you're going to saponify the ester, and that's just not good. So only use OH when you're doing aldol. Remember that. That's very important. Basically, we're just playing around with decarboxylations and getting you guys comfortable with seeing like malonic esters and acetoacetic esters, and then decarboxylating them and getting the products. So for the first one, they're pretty much just testing whether or not you can draw 6-methyl to heptanoan. Yeah, heptanoan. And so I went ahead and redrew that here. This is the base you're going to use. Notice it's the same thing. It's the basic form of this guy. And that's important because really those guys are going to swap off and interconvert. But you need it because you need to make this guy a nucleophile. This guy right here. And so once you've done that, you can add, I know I annotated it to make sure I got the right alkane or halogenoalkane from the bromine. And then once you've done that, you're just going to want to basically take off. Wait, have I done something wrong here? No, I haven't, because this guy corresponds to this guy. Cool. The important thing to remember here is that all of this is going to decarboxylate. So we use water and acid, and so that's going to change this ethyl group here into a alcohol. And then once we've done that, we're just going to use heat, and that'll basically take the entire thing off. It'll decarboxylate it so you get the formation of CO2. And yeah, that's an important reaction. They use it in like the Krebs cycle and stuff too. Fun fact. Or the citric acid cycle. Yeah. Anyway, any questions on that one before I move on? No. Cool. Second part here, we're starting with methylpropanoate, and then seeing if you can prepare this other thing they have written. They've went ahead and told you that it's going to involve a Claisen, and so you need to make sure that you include this as your base because you have a methyl ester this time. You need to make sure that you have the methyl oxide or whatever. And yeah, once you've done that, these two bad boys are going to react with each other. So one guy is going to turn into the nucleophile. That's like denoted with the blue highlighter. The other one's going to turn into an electrophile, as denoted with the yellow highlighter, as I've done in the past. And then remember, make sure you remember where this like little ethyl or methyl is coming from. So when you do this, you're going to get like this original orientation of the molecule is going to like twist down as it's like represented right here. Although technically it like twisted down and then it's shifted, it flipped because you're working on this side now, if that makes sense. But regardless, you need to remember, you can do your acid and water, and then you can decarboxylate with heat and release the CO2. And so this is like the intermediate from that first step that I went ahead and drew here. This is the symbol for intermediate. Fun fact. Hopefully you guys kind of start to pick up on that. If you're a chemistry major, you should probably remember that for later. But yeah, that's pretty much it. Any questions on this stuff?
How did you change the OCH3 before you added the acyl halide?
Okay, so where are you talking about?
Like here, let me see. I'd say like I guess between step 1 to 2.
Okay.
Because like what I did was, I took one of the alpha carbons and then made it negative, and then that attacked the same molecule or the same molecule,
Yeah.
and then did the movement of the electrons to get rid of the OCH3. So after you got rid of the OCH3 the first time, how did you change the OCH3 on the ester?
Okay. So you saying like this one should go away? Like
Yeah,
once.
how did you get rid of that one? How did you
Okay.
change?
Okay. I see what you're saying now. Okay. Sorry, it took me a minute to understand what you were saying. Um. So when that attacks, it'll look like this. And so when that guy is coming in, you're going to see that, let's see, first of all, these electrons are going to come up here, and then you'll get a
Right.
formation of like something right here. This guy is going to be like that. And then basically, these electrons are going to come back in from that intermediate state, and then these electrons are going to come back out onto this ethyl. Um, and so that'll cause this ethyl to come away. And so that's why you've only got one um, guy with an ethyl, one carbonyl group with an ethyl group in the intermediate here. Does that make sense?
Okay. Yeah.
So you see what I'm saying? All that's happening is if I take away all this, I'm attacking this, and something's got to come out, and so it's that guy.
Hmm.
Does that make sense?
Yeah. Because I saw like when I was doing this earlier, I saw one mechanism where it was a two-step. It was NaOH H2O and then the CH3 CH2 attached to a halide.
Gotcha. Yeah.
And then they did acid plus heat.
So that'll be the decarboxylation part, is the acid plus heat, but that's
Yeah.
different. I think that's probably saponification if you're using OH. But we'll talk about that more later in this thing.
Okay.
If y'all don't get saponification, we should probably go back and talk about that. But an important thing to remember, kind of moving on to these malonic ester synthesis, is once you've gotten out of this state where you've got your esters, there is an acidic hydrogen on the carboxylic acid, and that is like an actual acid. And so it's not just like pretty easy to remove that. It's like it's got a pKa of like around 5. So that means it's like 10 to the power of 15 times more likely to remove this hydrogen than to remove one of these bad boys. So once you've got it in this like state, I guess what I'm trying to say is once it's in that state, it's not gonna you're not gonna be able to play around with it as much. So you'll want to go ahead and decarboxylate from here. Because once you're here, or rather, see it as once you add acid and water, you're pretty much locking down whatever's at this carbon. Does that make sense? And so then part A just asks to show the electron movement for decarboxylation. You guys should hopefully be pretty comfortable with that. All you're making is CO2 from this bad boy on this side. And you can just kind of rationalize it as, it's making a circle. And then enol and enolate ion tautomerization, that's shown right here. That's pretty, you guys have been doing that for a while. And then for this last one, it's just asking you guys to like basically imagine if this compound was formed from malonic ester synthesis. And if both of these compounds were formed from that, what type of I guess substituent would you be adding with the halogen to add it, if that makes sense? And so to do that, you're going to want to use like any of these bad boys, whether it's propyl group with a Br or methyl group with a Br or like a phenyl group with a carbon spacer and then a Br. If you're comfortable with that, that'll make this recitation pretty easy. Moving on, I'm going to quickly compare acetoacetic ester and malonic ester. I kind of made this pretty and artsy. This is about as artsy as it gets for me. So malonic ester makes carboxylic acids. Hopefully you guys will see that it always makes carboxylic acids, and it'll always decarboxylate on one of these sides. Same thing for acetoacetic ester. It'll also decarboxylate the side guy off. But acetoacetic ester makes ketones. And so basically the only difference is there's this here on one side and then there's this on the other side. And, on the malonic ester side, that'll turn into carboxylic acid. And on the acetoacetic ester side, that's just like something that's there. It's a carbon. You can also do stuff with an R group here, and a lot of times you'll see fun chemistry with that. But that's not technically an acetic group, because acetic by definition is just like a carboxylic acid, and then there's one like methyl off to the side. So yeah, both of these have acidic hydrogens right around this vicinity, in between the two carbonyl groups. And then both of them can decarboxylate. And both of these, it's very important that you remember here, this is going to be kind of artsy. Don't use hydroxyl. And yeah, that's it. So we'll pretty much only be using mercuronic ester for synthesis. And it's the main one that we'll use for synthesis. Acetoacetic ester you can use to basically make any beta keto ester that you can imagine. And yeah, that's pretty much it for that. I'm going to stop recording. Any questions? Cool. Okay, so I'm going to go over the challenge problems now for the recording. So the first one here is just an aldol. So hopefully you see this right here and you recognize that you're going to need basically something that can be a donor. So this bad boy right here. And then all that you've got is just like one carbon over from this bad boy is your carbon with a hydroxyl. And so a good carbon with just a hydroxyl would be F. And so that'll be your acceptor. And so basically you're going to do an aldol. And then basically only one reaction away from that, you will be eliminating it. Somebody left a little comment thing. No, we're cool. Have a great weekend. Bye. Whoever's leaving. Acetoacetic ester. So this one is just a matter of recognizing that, like, basically, okay, give me a minute to think about how to talk about this. You're going to need to form this ring right here from two different like points. And so remember when we've got this bad boy, this acetoacetic esters, or all of these, whether it's malonic, acetoacetic, even aldol, there's two hydrogens available. And so you can reduce off both of those or eliminate them, I guess. And when you do that, you can fill that in for whatever you want and whatever you need. So for this second one, really, it's a matter of looking at all of the options and considering what's going to give you this starting point. And so then you're also going to need to make sure you include this part. And so from here, you can, for me, I just assume it's going to be acetoacetic ester because of how this will be easily reduced, and then this is easy to add. And so I guess you could see it as, well, not really any of these other ones would make sense. You're going to need to add something. I guess if you thought about E like they did earlier, that would technically work. It would just be a lot slower and wouldn't really be efficient because it's so hard to remove acidic hydrogens right here because they're not very acidic compared to when you have this whole big resonance system. Oh, okay, I'm just going to erase all this. And this whole big resonance system that gets created when you make this a negative charge. So yeah, that's that. Let's see what else. Well, it's not in, and I'm going to talk about that because that's what most people say. Because then you create a spacer carbon. It's also important to remember that throughout all of these that you're using for acetoacetic ester, malonic ester, that sort of thing, you're using the base, like the R group of whatever is with your ester as your base. And so after that, let's see. So if you were to do N, which is what most people said, um, you're going to see that you have one carbon here, and then you have a spacer carbon, and then it attaches to this carbon over here. And so if I were to draw that out, what that would look like is this product right here. This would be the intermediate from just this nucleophilic attack that I have up here. And so basically after that nucleophilic attack, you're going to have one carbon here and then another carbon here, which is not what your product is. It's not what you want. The stuff in brown is stuff that will disappear when you do your water and acid, which will turn it into an ester and then decarboxylate with just heat. And so you're left with just this product. And so if I compare these two products, once again, you're going to notice there's a spacer carbon there. And so the only way to go directly onto the like acidic hydrogens or the nucleophilic carbon, I guess there, is going to be a really long linear carbon that can attack on one side and then fill in on the other side. And so, yeah, that's all there is for that second one. That's kind of the hardest one here. The third one is just across clays and condensation. Once again, make sure you're not using OH because OH will saponify your esters, and that's no bueno. And then let's see. So it's important that you remember for these that the brown stuff will just fall away because when you do this attack, this will be the nucleophile and this will be the electrophile. And so, yeah, I mean, I don't really know what else there's to say about this other than, like, I guess this is here. And that corresponds to this over here. And then in the final product, this is the only part that's corresponds to this. Yeah, I don't know how else I could expand on that. Somebody left a comment. What's up, Ashley?
Just wanted to watch that one real quick, but thank you.
Sure. Yep. Have a good one.
You too.
Okay, now it's just me. Last one is malonic ester. And so this one, if I scroll back up here and look at it, it's a matter of counting the carbons. So you can see this and see this part right here and realize you're probably going to need to use one of these two. If you count your carbons, you'll get it. It's important that you include one of your starter bad boys with your product. And so because we have a carboxylic acid here, we're going to want to use malonic ester. And so that just means that we can decarboxylate this and do reverse esterification. And reverse esterification, they didn't decarboxylate it. But yeah, that's that. And that's that. Then you've just got to calculate or count your carbons. And so I did that at when I was presenting it down here. So in this one, you've got 1, 2, 3, 4, 5. And then you're like, oh no, the final product has 6. But voila, the 6th carbon is actually the nucleophilic carbon. So that's all for that 4th one. I hope that made sense for like the maybe 1 or 2 people that go back and watch this. This is the 5th one. It's an aldol. Aldol is the only one with these guys that you're going to want to use OH. All the other ones, it will saponify. I should have a counter on how many times I said that. Yeah, so this will form, I mean, it's just a matter of A and B coming together. I'm going to go back up here to kind of talk about it. But for this one, hopefully you notice that this bad boy is, this part right here is an alpha beta unsaturated ketone. And so it's just been combined with this big ring thing. And so you just got a negative charge here that punches in here. And then from there, you've got this bad boy, which is going to get, he starts off as an alcohol, and then that alcohol will just further be reduced all the way off, which I probably showed down on the 5th step. Yeah. So this is the product of that original attack from the hydroxyl. And then after that, you've just got the little hydrogen here that's going to fall in and yeah, make that into alkene. And that actually opens up this into a huge resonance system, which will very much incentivize that reaction to proceed or stabilize, I guess, the product. It'll pull the products through. So yeah, that's all for today. This is March 19th, Recitation 8. I hope you guys have a fantastic rest of your days.